The surface of Earth is ruled by oceans, covering 70% of our world. Yet the true horror begins far below, in places sunlight never reaches. At 11,034 meters down, pressure could crush steel, and 94% of all life hides in permanent darkness. We've mapped Mars more completely than these abyssal depths, but what really lurks in the most horrifying places in the ocean, miles beneath sea level? To answer, we must first descend, step by step, through a planet more alien than you think. Atros, Earth is a water planet in every sense. Oceans stretch across 70% of its surface, dwarfing the land masses we call home. This blue expanse shapes the climate, steers weather, and supports the cycles that make life possible. When viewed from space, the continents appear as scattered islands, almost insignificant compared to the vast swirling seas that connect them. Salt water dominates the story. Out of all the water on Earth, 96% is locked in the oceans, leaving only a thin film of fresh water for drinking, farming, and every land-based ecosystem. If all the planet's fresh water were spread evenly across the ocean surface, it would form a layer barely 1.25 meters thick, less than the height of a kitchen table. This razor-thin margin explains why droughts can devastate entire regions while the oceans remain seemingly endless and unchanged. Life itself is mostly aquatic. An estimated 94% of all living things are found in water, from the tiniest plankton drifting with the currents to the largest whales diving the open sea. Land animals, including humans, make up just a sliver of Earth's total biomass. Most of the planet's living space is not only underwater, but also cold, dark, and hidden from view. Sunlight, the energy source for almost all life, barely scratches the surface. Its rays can reach only about 100 meters down before fading into darkness. Beyond this point, the world turns black and silent. The majority of Earth's volume, kilometers of water stacked atop each other, exists in perpetual night here. Life must adapt to survive without photosynthesis, relying on drifting organic matter or chemical energy from deep within the Earth. Despite its size, the ocean remains a frontier. Scientists have mapped the surface of Mars with greater detail than the seafloor. The reasons are simple: crushing pressure, total darkness, and the sheer scale of the task. The ocean's deepest trenches plunge more than 11,000 meters down, and each descent reveals new mysteries. The numbers are staggering, but they only hint at the true scale and strangeness of the world beneath the waves. Descending through the ocean's layers, the limits of life and technology are measured in meters. At 40 meters, traditional pearl divers reach their maximum depth on a single breath. Down here, water pressure is already 4 times greater than at the surface, squeezing air from the lungs and testing the body's endurance. For centuries, these divers have risked blackout and decompression sickness for the promise of a single shell. At 200 meters, sunlight disappears. This is the edge of the so-called sunlight zone, the uppermost layer that supports the world's greatest blooms of phytoplankton. Here, the base of the marine food web thrives, feeding everything from tiny shrimp to blue whales. But below this boundary, photosynthesis ceases, and the ocean begins its long descent into darkness. The deepest a human has ever dived on standard scuba gear is 332 meters. In 2014, Ahmed Garber set this record off the coast of Egypt, spending only minutes at the bottom before a meticulously planned ascent that lasted hours. Past this point, survival without a submersible is impossible. The body cannot withstand the pressure, and the risk of nitrogen narcosis and oxygen toxicity rises with every additional meter. Emperor penguins, the deepest diving birds, regularly plunge to 565 meters in search of fish. They can hold their breath for up to 20 minutes, their bodies specially adapted to store oxygen and avoid the bends. These birds dive deeper than most submarines, navigating in pitch-black water beneath Antarctic ice. At 1,000 meters, the twilight zone ends. Almost no light remains. This is the realm of bioluminescence, where creatures generate their own light through chemical reactions. Some use it to lure prey, others to hide from predators. The water here is cold and heavy, pressing in at over 100 times atmospheric pressure. Military submarines are built for strength and secrecy, but even they have limits. The maximum safe operating depth for most is just over 1,000 meters. Beyond this, steel hulls would buckle under the strain and the ocean would claim anything unprotected by engineering. At 2,200 meters, sperm whales hunt giant squid in battles that remain almost entirely unseen. These dives last over an hour, with the whales relying on echolocation to find prey in the absolute dark. The squid, in turn, have evolved massive eyes to catch the faintest glimmers of movement. Here, predator and prey are locked in a contest of endurance, strength, and adaptation. Each of these depth markers is a milestone, a boundary defined by physiology, technology, and evolution. As the ocean deepens, the rules change. Familiar life disappears, replaced by forms shaped by darkness, pressure, and scarcity. The ladder of the deep is not just a measure of meters, but a record of what life can endure and what remains forever out of reach for most of the planet's inhabitants. Below 1,000 meters, the ocean becomes a world of scarcity. Sunlight is lost to the surface, leaving the deep in permanent darkness. Here, the only reliable food source is marine snow, a slow, constant rain of organic particles drifting down from above. This snow is made of dead plankton, fish scales, fecale pellets, and fragments of plants and animals that never made it back to the surface. Every flake is precious. As it falls, it's picked apart by bacteria and scavengers, growing smaller and less nutritious with each kilometer. By the time marine snow reaches the abyssal plain, little remains but crumbs and residue. Yet in a place where new energy is almost never created, even these scraps are the difference between survival and starvation. The journey of marine snow is relentless. It starts with a bloom of life in sunlit waters, explodes with the death and decay of countless organisms, and ends as a thin dusting on the seafloor. This slow trickle of nutrients sets a rhythm of life in the deep. Animals here have learned to wait. Some drift with open mouths, filtering the water for whatever passes by. Others bury themselves in the mud, emerging only when the snow falls thick. The pace is glacial, the competition fierce, and every meal is uncertain. But food is not the only challenge. The temperature in the midnight zone hovers between 1 and 4 degrees Celsius, just above freezing. This cold slows metabolism and movement, forcing animals to conserve energy at every turn. The water is thick, heavy with pressure, and the darkness is complete. In this place, vision is useless. Instead, life has evolved other ways to sense and survive. Without sunlight, the deep ocean glows with a different kind of light. Bioluminescence, chemical light produced by living organisms, becomes the language of the abyss. Tiny flashes, pulses, and steady glows cut through the blackness. Some animals use this light to attract prey, others to warn off predators or find mate. The reactions that create bioluminescence often rely on luciferin and luciferase, chemicals that combine to release energy as visible light. In some cases, bacteria living inside the host provide the glow, forming partnerships that benefit both sides. As bioluminescence is everywhere in the midnight zone, more than 3/4 of deep-sea animals are thought to produce a light in some form. For many, it is the only way to communicate or hunt in a world without day or night. Some create elaborate displays mimicking the faint shimmer of marine snow to lure curious prey. Others use quick bursts to startle predators or disappear into the darkness. In a place where food is rare and danger is constant, the ability to create light is both weapon and shield. The deep ocean is a study in extremes, cold, dark, and nearly empty. Yet through marine snow and bioluminescence, life finds a foothold. Every adaptation, from slow metabolism to glowing lures, is a response to scarcity and perpetual night. This is the backdrop for some of the ocean's strangest and most haunting creatures, shaped by a world where survival depends on making the most of every faint signal and falling scrap. Predators in the midnight zone have rewritten the rules of survival. In a world with almost no light and next to no food, every adaptation is a matter of life and death. The anglerfish, perhaps the most iconic hunter of the deep, is a master of this environment. Its body is small and unassuming, but from its forehead grows a thin, flexible spine tipped with a luminous bulb. This lure is not just a trick of chemistry. The light comes from colonies of symbiotic bacteria living inside the anglerfish's lure and producing a steady, ghostly glow. The fish itself cannot make this light. It relies entirely on these microscopic partners, a relationship forged over millions of years. The lure dangles in front of the anglerfish's cavernous mouth, swaying gently in the current. In the pitch-black water, the faint glow mimics the scattered flashes of bioluminescent prey or drifting marine snow. curious animals approach. Us wastes nothing, because in the deep sea, wastes nothing, because in the deep sea, every meal might be the last for weeks. But hunting is only half the story. Energy is precious in the abyss. Most predators here do not chase or fight. Instead, they drift on slow currents, mouths agape, conserving every calorie. The metabolic rates of these animals are among the lowest in the animal kingdom. Movement is slow, deliberate, and often barely perceptible. A single miscalculation, a wasted burst of speed, a failed attack could mean starvation. Dr. Karen Osborne, who has spent years studying deep-sea creatures, describes them as alien in their patience, their bodies gelatinous, and their movements almost dreamlike. Every adaptation is about not wasting energy. The anglerfish's gruesome appearance is another result of this trade-off. Its body is soft and flexible, able to withstand crushing pressure without wasting resources on bone or muscle. Some species are little more than a floating stomach with a mouth. Males, much smaller than females, fuse themselves to their mates, becoming little more than a pair of gonads. Another adaptation to scarcity, ensuring that when two anglerfish meet, reproduction is guaranteed. This drifting lifestyle is common across the midnight zone. Gulper eels, with their enormous jaws and whip-like tails, hang in the water column, waiting for something edible to pass by. Deep-sea jellyfish pulse slowly, spreading their tentacles to catch whatever the current brings. Even predators, like the giant squid, known for their battles with sperm whales, spend much of their lives drifting in the gloom, conserving energy for the rare moments when they strike. The result is an ecosystem where patience is the ultimate weapon. Here, the line between hunter and scavenger blurs, and survival depends on making the most of every scrap. The midnight zone is not empty, but it is unforgiving. Every adaptation of glowing lures to symbiotic bacteria is a testament to the relentless pressure of life at the edge of the possible. At a depth of 6,100 meters, the ocean floor stretches out in a vast, featureless plain. This is the abyssal platform, a region that covers more of the Earth's surface than all the continents combined. The temperature hovers just above freezing, and the pressure is nearly 600 times greater than at sea level. Here, the seafloor is mostly soft sediment, punctuated by occasional outcrops of basalt or manganese nodules. The plain seems endless, but it is anything but stable. Tectonic plates meet and grind beneath this quiet expanse, creating zones of relative calm and areas prone to sudden upheaval. Despite its apparent emptiness, the abyssal plain is a critical setting for modern life. Most of the world's internet cables are laid here, snaking across thousands of kilometers to connect continents. Engineers choose these depths because the terrain is generally flat and less likely to be disturbed by fishing trawlers or anchors. But the plain is not immune to natural hazards. Earthquakes can trigger submarine landslides, sending torrents of sediment racing across the bottom. In 2006, an earthquake off Taiwan severed multiple cables, disrupting communications across Asia. These events are rare, but their impact is immediate and far-reaching. The geological forces at work are immense. The abyssal plain sits atop tectonic plates that move only centimeters per year, but the energy they store can be released in seconds. Some regions are considered tectonically stable, offering a safer route for cables. But others are marked by fault lines where the risk of sudden shifts is much higher. Landslides triggered by quakes or the slow buildup of unstable sediments can bury cables under meters of debris or drag them for kilometers. Even without such disasters, the plain is shaped by slow-moving currents and the steady rain of marine snow, which over millennia builds thick layers of mud and silt. For all its dangers, the abyssal plain remains the best option for laying critical infrastructure. When its vastness provides room to spread out, and its relative flatness allows cables to be placed with precision. But every route is a compromise, balancing the need for stability against the unpredictable power of the deep. The geology of the plain sets the stage for everything that follows, grounding human technology in one of the most remote and unforgiving environments on Earth. At the bottom of the abyssal plain, a hidden network carries the world's conversations and commerce. Oyas, over 400 active subsea cables snake across the seafloor, forming the backbone of international communication. These cables, as thin as a garden hose but stretching for thousands of kilometers, transmit more than 99% of global internet and phone traffic. Every email, Video call and financial transaction between continents depend on these fragile threads, resting in darkness 6,000 meters down. The choice to lay cables here is deliberate. The abyssal plain is flat and remote, away from the chaos of coastal shipping lanes and the scraping of trawl nets. But the deep is not without risk. In 2006, a powerful earthquake off Taiwan triggered submarine landslides, severing 8 major cables in minutes. The disruption rippled across Asia, cutting off banks, businesses, and families from vital connections. Engineers scrambled to reroute traffic and deploy repair ships, but some regions waited weeks for full service to return. Cable failures are not always natural. The ocean floor is a patchwork of jurisdictions, and the cables themselves are tempting targets. Accidental damage from anchors and fishing gear remains common, but recent years have seen a rise in concerns about sabotage and espionage. Governments and industry groups debate how much to reveal about cable locations and how closely to monitor their integrity. Real-time sensors and acoustic alarms can spot damage early, but sharing this data means exposing vulnerabilities to potential adversaries. Confidential memos from telecom companies highlight the tension. Security demands secrecy, but reliability needs transparency and international cooperation. For the engineers who design, lay, and maintain these cables, the stakes are personal. One archival note from a cable-laying chief engineer, written after a storm nearly snapped a Pacific link, reads, "We are custodians of the world's nervous system. Any break are anywhere, and the world feels it instantly." Every day, billions of people place their trust in a web of glass and steel buried beneath the coldest, darkest waters on Earth. The abyssal plain is not empty. It is a lifeline, fragile and fiercely contested, linking human society across the planet's last great frontier. The Pacific Ocean hides its most astonishing secret beneath a scar in the seafloor that stretches for over 2,500 kilometers, the Mariana Trench. This trench is not a crack or a canyon, but a vast crescent-shaped chasm, deeper and longer than any other on Earth. Its formation begins with a relentless process. The Pacific Plate, massive and ancient, is slowly forced under the smaller Philippine Plate. This subduction zone acts like a conveyor belt, dragging the oceanic crust downward and bending it into an arc that plunges into the planet's mantle. The result is a trench so deep that if Mount Everest were dropped into its deepest point, often known as Challenger Deep, the mountain's summit would still be hidden by more than 2 kilometers of water. The Mariana Trench's dimensions defy everyday comprehension. At its widest, it spans nearly 70 kilometers, enough to swallow entire cities. Its length, over 2,500 kilometers, rivals the distance from New York to Denver. But it is the depth that commands all. Challenger Deep has been measured at between 10,920 and 11,034 meters below sea level. That is more than 11 kilometers, almost 7 miles straight down. The pressure at the bottom exceeds 1,000 times the atmospheric pressure at the surface, a force so great that it would crush any standard submarine like a soda can. This trench is not a static feature. The plates that create it are in constant grinding motion. Every year, the Pacific Plate slides a few centimeters farther beneath its neighbor, deepening the trench and sending tremors through the surrounding seabed. These movements can trigger earthquakes and tsunamis, their energy unleashed from the hidden boundaries far below the ocean surface. The trench's walls are steep, sometimes nearly vertical, and the seafloor at its base is a narrow, V-shaped valley filled with fine sediments and scattered boulders. The sheer scale of the Mariana Trench challenges the imagination. It is a world apart, a place where the rules of geology, physics, and biology are rewritten by depth and pressure. For centuries, its existence was only hinted at by the patterns of waves and the readings of early depth soundings. Today, sonar mapping and robotic probes have revealed its true contours, but standing at the edge of this abyss, if it were possible, would be like gazing down from the lip of another planet. The trench is an enduring reminder of Earth's restless geology, a boundary where continents are born and destroyed, and a symbol of the ocean's power to shape the very bones of the planet. When at the edge of the abyss, the ocean transforms into a landscape shaped by forces that seem almost supernatural. At 10,809 meters, the Siren Abyss plunges deeper than nearly any other place on Earth, its slopes lined with sediments that have never seen sunlight. But even these depths cannot match the chemical violence found elsewhere in the trench. Near the summit of Daikoku Seamount, at just 414 meters, A molten sulfur lake bubbles and steams, one of the rarest environments on the planet. Here, liquid sulfur boils at temperatures few life forms can withstand, releasing toxic clouds and staining the water with a sickly yellow glow. This lake is so extreme that only a handful of known sites like it exist anywhere on Earth, and most are buried deep underground, not exposed to the open ocean. Deeper still, at around 1,600 meters, hydrothermal vents known as black smokers erupt from the seafloor. These chimneys spew jets of water heated up to 450 degrees Celsius, hotter than molten lead, yet under such immense pressure the water does not boil away. Instead, it blasts out in thick, mineral-rich plumes, instantly turning the surrounding water into a chemical soup. These vents are natural laboratories where elements like iron, sulfur, and manganese combine in ways that would be impossible at the surface. Dr. Chris German, a pioneer in vent exploration, once called black smokers the most alien places on Earth. Natural chemical labs where the rules of life are rewritten. The pressure in these environments is almost beyond comprehension. At Challenger Deep, the bottom of the Mariana Trench, the weight of the water above exceeds 1,080 bars, more than 1,000 times the pressure at sea level. Any unprotected object would be flattened instantly. Human bones would be crushed, steel would bend, and even titanium submersibles must be engineered to the limits of material science. Every descent is a test of both nerve and technology. In these hellish settings, life does not follow familiar patterns. Microbes thrive on chemical energy rather than sunlight, feeding on hydrogen sulfide and methane that seep from the vents. Some of the animals here, giant tube worms, blind shrimp, and heat-tolerant crabs, harbor bacteria in their tissues, forming partnerships that let them survive where nothing else can. The chemistry is so intense that the water around these vents can turn acidic and minerals crystallize out of solution in seconds, building towers that reach several stories high. These extremes explain why deep-sea exploration remains so hazardous. Every expedition to the trench or its vents is a gamble against pressure, temperature, and chemical toxicity. The rewards are profound. Each dive reveals new forms of life and new rules for survival. But the cost of a mistake, even a small one, it is total. The ocean's deepest places are not just distant, they are actively hostile, shaped by forces that challenge the very definition of what it means to be alive. In January 1960, the bathyscaphe Trieste began its descent into Challenger Deep. Don Walsh and Jacques Picard watched as the pressure gauge climbed past 1,000 atmospheres. At 10,918 meters, the craft touched the bottom. For 20 minutes, they peered through a small window at a landscape of pale silt and scattered rocks. Then something unexpected appeared. What Picard described as a flatfish, almost 30 centimeters long. The sighting was logged, sparking decades of debate. Could a vertebrate survive such pressure, or had they glimpsed a large invertebrate, distorted by the gloom and sediment? The question remains open, but their direct testimony stands as a rare record from the deepest point on Earth. 35 years later, the Japanese probe Kaiko reached 10,911 meters, this time without a crew. Its robotic arms scooped up sediment, revealing thriving microbial life. These extremophiles endured crushing pressure and near-freezing temperatures, their existence rewriting the limits of biology. Genetic studies showed unique adaptations, pressure-proof enzymes, compact cell membranes, and metabolic pathways tuned for survival in total darkness. Keiko's samples proved that life could flourish in places once thought sterile. In 2012, James Cameron piloted the Deep-Sea Challenger to 10,908 meters. Alone in a cramped sphere, he spent hours collecting samples and filming the seafloor. His sub suffered a hydraulic leak threatening to end the dive, but he managed to gather evidence of amphipods, sea cucumbers, and dense mats of bacteria. Cameron's footage and specimens confirmed that the trench is far from lifeless. Each expedition, Trieste's human observation, Keiko's microbial discovery, Cameron's high-definition survey, Osterk adds a layer of proof that the deepest ocean is alive and that its mysteries are only beginning to surface. The Puerto Rico Trench, concealed beneath the Atlantic, drops to 8,376 meters at the Milwaukee depth, a meeting point of tectonic plates marked by violence and mystery. In 1918, a magnitude 7.3 earthquake near its rim triggered a tsunami that swept away neighborhoods on Puerto Rico's coast, killing over 100 people, but the trench's secrets run deeper. NASA satellites have detected a gravity anomaly here, a subtle dip in Earth's pull, likely shaped by dense rocks and the trench's unusual structure. For geophysicists, it's a puzzle that hints at hidden forces still at work beneath the Atlantic. Life endures in these depths. Amphipods and sea cucumbers survive at the trench's bottom, enduring crushing pressure and cold. Yet the Atlantic's tidal zone remains largely uncharted, its biological mysteries locked away by depth and distance. Far across the globe, the Kermadec Trench, northeast of New Zealand, plunges to 10,047 meters. Here, researchers have found giant amphipods, scavengers reaching 34 centimeters, along with deep-sea snailfish and pearlfish, species that defy expectations and expand the boundaries of what life can endure. Human fingerprints reach even these remote places. Microplastics have been discovered in sediment cores and inside amphipods from both trenches. Synthetic fibers and chemical residues drift down with marine snow and sinking debris accumulating in the Hadal zone. Dr. Alan Jameson's team found plastic debris nearly 11,000 meters deep, shattering the myth of untouched ocean wilderness. Each sample ties the fate of the planet's most remote places to everyday choices. Despite these discoveries, less than a quarter of the ocean floor has been mapped in detail. The Seabed 2030 project aims to fill this gap, but progress is slow. The deeper the search, the clearer the connection between natural violence and human neglect. The Mariana Trench plunges to 11,034 meters, deeper than Everest is tall, making it the most extreme environment on Earth ever reached by humans. Since the Trieste's 1960 descent, every probe and sample has confirmed life's resilience, with organisms thriving at pressures over 1,080 bars and temperatures near freezing. Yet, even here, microplastics and industrial chemicals have been detected, are proving that human impact knows no boundaries. Today, over 80% of the ocean floor remains unmapped, and much of the Hadal world is unexplored. Scientists still debate how deep life can persist, and the full consequences of deep-sea pollution are not yet known. As global reliance on subsea cables grows, the vulnerabilities of these abyssal depths directly affect modern life. The evidence is clear. Earth's darkest places are not empty voids, but vital frontiers, rich with unknown species and bearing the marks of human presence. Our understanding remains incomplete, but the facts demand continued exploration and responsibility.